Greetings, physics enthusiasts. I would like to welcome you to, what is this? This is AP Physics 1, Unit 1, Lesson 11. So welcome to Lesson 11. In this lesson, I would like to start by reminding you of the format that every projectile motion problem follows. So every projectile motion problem involves thinking about an object that travels along this parabola. And the parabola continues forever down and right, and it also continues forever down and left. It doesn't continue forever up. And that becomes significant later, that there are some heights the parabola does not reach. But it does go on and on and on, down and left. It does go on and on, down and right. Sometimes in the problem, the ball will start here, in which case the ball's initial velocity, pardon me, is up and right. Sometimes the ball starts here, in which case the ball's initial velocity is straight to the right. In problems where we throw something horizontally, or where something is rolling along on a table and then the table ends. Sometimes the ball starts out over here. The ball starts out going down and right. If you're at the top of a building and you're throwing something down to someone on the ground, the initial velocity is down and right. The velocity vector is always tangent to the parabola. But every problem has this parabola. And what you want to do is you want to identify where on the parabola the projectile begins and where on the parabola the projectile ends. It could start here and end here. It could start here and end here. It could start here and end here. It could start here and end down here. Or it could start here and end here. Or it could start here and end here. Lots of different possibilities. Regardless, the horizontal description of the motion is always placed here on the left. Vx times t equals x. And that horizontal speed is always the initial speed, not the initial velocity, but the initial speed times the cosine of that angle, the original direction, times t equals x. So Vx, the horizontal speed, is the diagonal original speed times the cosine of the angle. Over here on the right, we always describe our vertical motion. Y, the vertical displacement, A, the vertical acceleration, T, the time, Vy initial, and Vy final. The vertical speed at the beginning, the vertical speed at the end. A is always negative 9.8, and this t and this t are the same. So it is very common for us to find the vertical time and then use it over here in the horizontal equation, or to find the horizontal time and use that same number over here. Vy initial is always V naught sine theta. So one of these is sine theta, one involves cosine theta. All right, and then depending on where we're starting and where we're ending and what question is asked, we're going to fill in. So that's just what I wanted to remind you of, that all of our projectile problems look like that. Now, a lot of times over the last couple of weeks, people have asked a question. Can you help me with number whatever? Can you help me with number 17? And I'll say, sure. But because I'm old and because I haven't read number 17 in the last 5 minutes, I often don't remember what 17 is about. So I will say to you, tell me about number 17. Now, another reason I ask you, little insight into my mind, another reason I ask you to tell me about number 17 is I'm interested in, have you read the problem? I hope you haven't just said, oh, he assigned number 17, I'll ask him for help with number 17. But Some, 17 is, it's a problem. It's four sentences. It's a whole paragraph. And maybe you've read that paragraph 2 or 3 times, but do you understand what it's saying? And that's more of a literacy thing than a physics thing. But let me give you an example. One of the problems from last week was this number 22. So this says, one of the fastest recorded pitchers in Major League Baseball, thrown by Billy Wagner way back in 2003, was clocked at 101 miles per hour. See the figure. Okay. There is a lot of words there, and none of it matters. So one of the things I'm wondering is, are you just going to read me all this stuff that doesn't matter? Hopefully not. If a pitch were thrown horizontally with this velocity, how far would the ball fall vertically by the time it reached home plate 60.5 feet away? Okay, so that's a lot of stuff. And then there's a picture of this person who played for the Phillies. So if I were to say to you, what's going on in problem 22? I don't want you to tell me that it's Billy Wagner, or that he wore a red shirt, or that he played for the Phillies, or that it happened back in 2003. None of that matters. What I want you to tell me is the ball starts here. How do I know the ball starts there at the vertex? Did you catch it? Because it told me in the problem the ball was thrown horizontally, which means the ball starts there. And then the ball ends over here somewhere at home plate. I don't care that it ends at home plate. I just care that it ends somewhere later on. So the ball moved down and the ball moved to the right. And they told you one of these distances and they asked you to find the other. Did you notice that? They told you this distance, x equals, that was given, it said 60 before it reached home plate, 60.5 feet away. That was given, and y equals question mark, that's the answer. So when I say to you, when you say to me, can you help me with number 22? And I say, sure, tell me about 22. What I want you to tell me is, well, there's a ball and they tell me it's thrown horizontally and then it travels down and to the right along a parabola. They tell me how far it goes horizontally. They want me to find how far it goes vertically. Oh, and they told me this speed as well. Now, I don't want you to tell me the speed. I don't want you to tell me the distance. None of that matters. But if you know what's going on in a problem, you should know they gave us the original horizontal speed. They gave us how far it traveled horizontally, its horizontal displacement, its range. And the point of the problem is to find the vertical displacement. That's the kind of thing I'm looking for. The other thing that's important on this problem is that they gave you original information in what I call stupid units, 101 miles an hour. Don't worry, just say to Siri, convert 101 miles an hour to meters per second.
That would be 45.15 meters per second.
That wasn't hard, right? And convert 60.5 feet to meters.
It's 18.44 meters.
So Siri can just do those conversions for you very, very fast. Don't even write these down on the paper. Just convert them to the right unit and write those on the paper. Save yourself some work. All right. So now what I'm going to do for the rest of this video is I'm going to do an example projectile problem. Am I going to do 1 or 2? Oh, I'm just going to do one example problem. So to do an example problem, I'm definitely going to need this picture of a parabola. I'm going to need my horizontal space to do work, and I'm going to need my vertical space to do work. I haven't even told you what the problem is yet, but I know I'm going to need this. Vxt equals x, initial cosine theta times t equals x. Do you know why I put the parentheses there? Because I don't want you to multiply theta by t before you take the cosine. Okay, and then vertically, y, a, t, by initial, by final. And I know a is negative 9.8, and by initial is the initial sine theta. Okie dokie. So in this problem, I'm going to tell you the original conditions. I'm going to tell you the ball's initial speed and the ball's initial direction. So given V naught and theta, I'm going to give you those, and I'm going to ask you for time to reach a certain height. So, instead of saying the ball is thrown straight up at a certain speed, how long does it take to get 3 meters high? I'm going to say, the ball is thrown diagonally in a certain direction at a certain speed. How long until it reaches a specific height? All right. So let's do that. A ball is thrown at 35 meters per second. 75 degrees above horizontal. So in other words, this angle is 75 degrees, and this arrow, this diagonal arrow, is 35 meters per second long. Find t, find the time it takes to reach a height of, let's say, just a sec, 40 meters. It's pretty high. So a ball is thrown at an original speed of 35 meters per second, 75 degrees above the horizontal. Find the time it takes to reach a height of 40 meters. So let's fill in. I'm changing colors now because now I'm solving the problem. V initial is 35 and theta is 75. Cos 75. T is the answer. I can't find that because I don't know x. So maybe that's not going to be very useful. Over here, V initial is 35 sine 75. All right. And I want to find t, that's my question mark, when I want the height to be 40 meters. So y final is 40. I'm assuming my original, I'm calling my original height 0 and my final height 40. Now, you might be wondering, well, where's the end? Is the end here? Is the end here? Is the end here? We don't know yet. Sometimes when I throw something, its maximum height is 40, in which case we get to that height once. Sometimes if its maximum height is 50, it gets to 40, and then it gets to 50, and then it gets to a height of 40 again. So I might get to a height of 40 once, if that's the maximum height. I might get to a height of 40 twice, 40, and then the maximum height, and then 40 again. Or it may be, what if the maximum height is 30? Then when do I get to a height of 40? Never. So I might get no times when I reach a height of 40, if it doesn't go that high. I might get 2 times that I reach a height of 40, or I might just get 1 time that I reach a height of 40. Let's see how I'm going to figure that out. I have a number, I have a number, I have a number. Whenever I have 3 numbers, number, that's a good thing. That's a good thing because my kinematic equations have 4 variables. And if 1, 2, 3 of them are numbers, I can find that 4th one that's a variable. So turns out Vy final isn't so important here. So I'm going to write the kinematic equation that does not contain Vy final. And that kinematic equation is x equals v initial t plus 1/2 a t squared. And I'm going to plug in this vertical information into this equation. So x now becomes y, 40 equals Vy initial 35 sine 75. 35 sine 75 times t plus 1/2 a. Half of negative 9.8 is minus 4.9 t squared. I'm going to rearrange that so that the negative t squared becomes positive and it's on the left, so that this positive thing, 35 sine 75 t, becomes negative on the left and the 40 stays on the left. And then I just have 0 on the right. So I've got 4.9 t squared minus 35 sine 75 t plus 40 equals 0. And so this is a quadratic equation where 4.9 is A, negative 35 sine 75 is B, and 40 is C. So the quadratic formula tells me that my two values of t are t equals negative b. That's 35. B is negative, so I'm going to make negative b positive. 35 sine 75 plus or minus the square root of b squared. 35 sine 75. That whole thing squared minus 4ac all over 2a. 2 times 4.9 is 9.8. All right, and I'm just going to stick that in my calculator. You know, maybe not the easiest sticking into the calculator ever, but I can do it. So let me do that for you real fast here, and we'll see what that looks like. I'm going to look at this part first. 4 times 4.9 times 40, 784. Okay. And then I'm going to change the sign and make that negative because it says minus that. And then I'm going to do sine 75, take the sign, times 35. And then I'm going to square that. 1,142. And I'm going to add that to the negative number I had before, and I get 358.9. And then I'm going to take the square root, and I've got this 18.9457. We'll just call it 18.9. So 18.9. So basically I have plus or minus 18.9 over 9.8. 35 sine 75. 75 sine 35 times. There we are. 33.8. 33.8. And what's nice at this point is I can see 33.8 plus 18 is about 50. Divided by 9.8 is about 5. So around 5 seconds. 33.8 minus 18.9 is about 15. 15 over 9.8 is, around 1.5. So I'm going to reach this height of 40 twice at about 1.5 seconds, and then again at about 5 seconds. So I can figure those out nice and tidy, and I can say, at what time does it reach a height 40 meters? 2 different times. And those 2 different times are about 1.5 seconds and 5 seconds. And you can find them very specifically and accurately. But what I want to call your attention to is this part right here, the square root. The stuff inside the square root. Ooh, if this had been bigger or this had been smaller, it's possible for these two parts to have been exactly the same size. If they were exactly the same size, then something minus something exactly the same size is 0. And in that case, this plus 0 and this minus 0, same thing. That when these two are the same as each other, when what's inside the square root is 0, we call that the discriminant in your math class. That corresponds to us reaching that height right up here at the vertex. And we only reach that height one time. Sometimes I get two values of t when I add 18.9 and when I subtract 18.9. Sometimes I only get one value of t if this part happened to equal 0. Ooh, isn't that cool? Sometimes if I say, hey, this height up here of 500 meters, it never gets to a height of 500 meters. That's ridiculous. So if I'd asked about that 500 would have gone here. That 40 was the height. If instead this had been 500, this negative part would have been too big. I would have had a number minus something, and what's inside the square root would have been negative. And when what is inside the square root is negative, I can't take the square root of a negative number. I get something imaginary. And therefore, that's the equation's way of saying it never gets that high. So that's when I have no answers. So if what's inside the square root is negative, there is no answer. It never gets that high. If what's inside the square root is the number 0, that one magical moment right here, I reach that height one and only one time. And that height happens to be the vertex. Or if what's inside is positive, then I'm going to add that square root and I'm going to subtract that square root. And I'm going to get the two different times I reach that height. Does that make sense? So I just wanted to show you how to do all the steps, how to use the calculator, and the different possibilities you might have, depending on what numbers actually go in here. You might get an imaginary number. The thing doesn't happen. You might get a 0 in here. Yay, we're talking about the vertex. You might get two numbers in here. Yay, we're talking about two special points of the same height on the parabola. I hope that clears a few things up that you've been wondering about, and I hope you're having a wonderful weekend. I will see you soon in class. Bye-bye.